Hello, I am 3STEM. We've been talking about sequences and series, and specifically arithmetic and geometric sequences and their related series. In arithmetic and geometric, we talked about finding the finite sum of the first n terms in addition to finding the infinite sum of a geometric term when the absolute value of the common ratio is less than 1. We've also introduced you to summation notation in order to have a way to express strings of terms representing the series of expressions. We'll be relying on this more, so you need to remember we use I and call it the index of the summation and use n to identify the upper limit of the summation. And that I equals 1 talks about the lower limit of the summation. So in this lesson, and ones that follow, we'll be focusing on sums of terms of sequences that are not only arithmetic or geometric. In particular, we'll be introducing the idea of expressions that are sums of polynomial series. As we combine the ideas of the properties of sums and a list of sums of powers, we'll exercise your skills in algebra in this week's homework. So as we get into talking about our summation notation, I want to remind you that I is our index, and so as I say a sub I, we're talking about particular terms as I is increased in its index. So I equals 1 is the lowest limit of what I can be, and n identifies what the highest point that I can be. So if we're talking about then this summation in particular, we're talking about a sub 1 is going to be our first term, and that added to a sub 2, the second term, and that added to the third term, a sub 3, and added to a sub 4 plus dot dot dot, and keep on going until we get to a sub n as the nth term. So we're talking about that, but we're also talking about different properties of sums as we can express them. So the very first one that we want to talk about is one when c is a constant. So let me just go ahead and draw an instance that looks like number 1. So we have our summation, the sigma, and we have I is equal to 1 to n. And let's use, instead of c, we'll use 3. So as we do this, the first term, since there isn't any operator on I, the first term is just simply going to be that constant 3. And the second term is going to be that constant 3. And the third, and on and on and on, until we get to the nth term, and that's just 3. So all the terms are 3. So isn't this the same as saying 3 times n? Because we have n instances of 3 being added. And so there it is. In the first property, the sum of c is just going to be c times n. In the second case here, notice we have an expression that looks like this. And I'm going to give you an illustration. So I is equal to 1, and we're going to the nth term. And let's say we're just talking about 2 times I. So isn't that going to expand out this way, where that's going to be 2 times 1 for the first term, and that added to 2 times 2 for the second term, and that's going to be added to 2 times 3, and keep on going until we get to 2 times n. Well, couldn't that just be the same as saying 2 times 1 plus 2 plus 3 plus dot 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 plus n? Which is the same as saying, couldn't we just say then instead 2 times the sum of I? So that's why we're able to just pull that out. It's just using the distributive property. So in the third case, we're talking now about two different expressions, an a sub I and a b sub I. And so if I'm taking the sum of a combined set of expressions, that I can actually separate those expressions and say this is the sum then of a plus the sum then of b. And similarly with a difference, we can say we're talking about the sum of a minus then the sum of b. So what we're focusing on is this idea that we can come up with these expressions that are on the right-hand side when we finally found the sum. And that's what we're going to be working on today. So before we move any further, I wanted to remind you of some of the formulas that are related to sequences and their sums. So to start with, if we're talking about an arithmetic sequence, of which is the foundation of an arithmetic sum, we have to know our nth terms in certain cases. So you remember then that explicitly we can find a sub n by taking a sub 1 and adding the common difference d times n minus 1 in order to find the nth term. And then you simplify that down in order to just have a formula to work with. If you're going to go recursively, and we know what a sub n is, but we want to know what a sub n plus 1 is, then you know that all you have to do is add the common difference. If we're going to talk about the sum of a finite arithmetic sequence with n terms, then hopefully you remember that S sub n is equal to n divided by 2, and that times the first term, a sub 1, plus the last term, a sub n. And moving on, if we're going to find the nth term of a geometric sequence, using an explicit expression now, we're talking about a sub n is equal to a sub 1 times r, which is the common ratio, raised to the n minus 1 power. And you can use that and then simplify that expression in order to get something that you're working with per the sequence. If you're going to talk about recursive, we want to know what a sub n plus 1 is. When we know what a sub n is, you realize that all you need to do is multiply by the common ratio, r. And then we describe to you the formula for a finite geometric sequence. S sub n then is equal to a sub 1 times the difference 1 minus r to the nth power divided by the difference 1 minus r. Now that's finite. And then we also came up with the idea that we can take the sum of an infinite geometric sequence if the absolute value of our common ratio is something less than 1. And so that just is taking the finite geometric sequence and boiling it down to S now is equal to simply a sub 1 divided by the difference of 1 minus the common ratio. In this next slide, we've titled this Sums of Powers of Integers. Now the integers being the terms themselves, but we're taking the integers now to the power. So this is to the first power, this is to the second power, this is to the third, fourth, and fifth. Now the reason why this is highlighted right here is because this would be handy to memorize these things because these are expressions that you are going to be using in calculus. This actually is a photo of a page, of a part of a page coming out of the purple book on page 386. And so if you want to refer to it there, that's where you can find it. But it's going to be helpful to you to at least recognize that these are the sums of those terms. You should recognize this one because this is an arithmetic sequence, 1, 2, 3, etc. to n, and that's just simply n times n plus 1 over 2. That was when we talked about Carl Friedrich Gauss. So moving right along, if we were talking about squared terms now, and this would be quadratic now, then the sum ends up being n times n plus 1 times 2n plus 1, and all of that divided by 6. If we're doing to the third power, n to the 3, that becomes n squared times n plus 1 squared over 4. And if you wanted to talk about the n to the fourth, now we're talking about n times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1, and all of that divided by 30. For the fifth, n to the fifth, well, you can see it's n squared times n plus 1 squared times 2n squared plus 2n minus 1 over 12. But what we're going to be doing in the homework today is working on these first three. Here in example 1, we want you to use the properties of sums and the sums of powers to find the sum of the first n terms of the polynomial expression. So here we have this polynomial expression, a sub n is equal to n squared plus n plus 1. And those are the terms of the sequence. And so we've got a sub 1 then is going to be 1 squared plus 1 plus 1. And that's just 1 squared is 1 plus 1 plus 1, that's 3. And a sub 2 then is going to be 2 squared plus 2 plus 1, and that's equal to 2 squared is 4 plus 2 is 6 plus 1 is 7. And a sub 3 is going to be 3 squared plus 3 plus 1. 3 squared is 9 plus 3 is 12 plus 1 is 13. And we're going to keep on going like that. I think that you get the idea. But this is what I'm wanting you to see, is that we're saying S sub n, which is the sum of all of the first n terms, is going to be then 3 plus 7 plus 13 plus ... plus, and we now have the a sub nth term. We're also being told that we can come up with an expression that summarizes this S sub n, just like we saw Carl Friedrich Gauss come up with the sum of an arithmetic sequence. So this is what it's going to look like. You see S sub n then is going to be, using summation notation, with an index of I is equal to 1, and we're going to talk about going to n, of I squared plus I plus 1. But the properties of sums tells us that we can say it this way, that I can duplicate this summation and actually make it 3 terms. And the terms are going to look like this, that this is I squared plus, and this one's going to be I, and plus, and this one's going to be 1. When we come up with the expression that is each of these summations, we write this in n because we're allowing I now to reach the nth term, and we're saying it this way. So we know that I squared comes out looking like this. n times n plus 1 times 2n plus 1 divided by 6 plus, and we know that the summation for I turns out to be n times n plus 1 divided by 2. And we know that the sum of a constant is just going to be 1 times n, so that's n. Let's take a look at this and clean it up a little bit. So we're going to shrink this down. And let's write this properly. We're going to factor this out. You could actually finish with this statement right here and say that this is my S sub n. But we want to clean it up a little bit to make it look like one solid term. I'm going to start with factoring out things that I can factor out. I see an n in each one of these terms, and I also see a greatest common factor in the denominator is 6. So I'm going to factor out an n over 6. Now, for the first term, that's just going to look like this now. What's left over is n plus 1 times 2n plus 1. And the second part now, we need to actually multiply by 3 in order to make a 6 down below. And we got to do that on top and bottom. And for that matter, for this n, we got to put a 6 down below. That means we got to put a 6 on top. And so as we're factoring out n over 6, notice what we're doing. This ends up being plus 3 times n plus 1 plus, and we factored out that n, and so this one becomes just 6. So now let's just work inside the parentheses. N plus 1 times 2n plus 1 becomes 2n squared plus 3n, because that's n times 1 plus 2n times 1. And then 1 times 1 gives me the 1. And then this next one, we just distribute that 3, and so we get plus 3n plus 3, and then plus 6. We have 2n squared, and let's combine the like terms. So we got 3n plus 3n becomes 6n. And then we have 1 plus 3 plus 6. That is 10. And we have n over 6. Now we happen to notice that there's a common factor of 2 inside each of the terms inside the parentheses, so let's pull that out. And so that becomes 2n over 6. Well, that just becomes n over 3. And now we look like this, n squared plus 3n plus 5. And that's a polynomial that can't be factored, and so we're done. So there's our expression of S sub n, the sum of the first n terms of our original expression, a sub n is equal to n squared plus n plus 1, and that's equal to S sub n equals n over 3 times the polynomial n squared plus 3n plus 5. Now, before we get into example 2 and 3, I want you to look at this list of things that I want you to know how to do. I want you to find a formula for the nth term, because in some cases we're just going to be giving you numbers and plus signs and expecting you to come up with what a sub n must be. So we're going to do that. And then B is to rewrite that formula in sigma notation. And you saw me do that in example 1. And then find a formula for the nth partial sum of S sub n. So those are the 3 things, and the reason why I'm showing you this is because your homework is going to be exactly this. There's going to be 12 problems where you're going to have to answer all 3 of these parts. So let's take a look at how things look when we do example 2. Because this one says find a formula for the nth term. If the nth term is 1 times 3 times 5 plus 2 times 4 times 6 plus 3 times 5 times 7 plus, and on and on and on. Well, let's take a look and see what that must be. If you look at this carefully, you see 1 times 2 times 3 times 5. Now, hold on a second. I see 1 here, I see 2 here, and I see 3 here. And what's going on here? Well, this is going to be 1 plus 2, and then this is 1 plus 4. And isn't this 2 plus 2 and 2 plus 4? And this is 3 plus 2 and 3 plus 4. So, couldn't we write this way? Then instead of the first term or the second term or the third term, let's say the nth term. Wouldn't that be then n plus 2 and then times n plus 4. And so there it is. There's my a sub n. That's what it looks like. And so that's the nth term of a sub n. We're going to rewrite this now in sigma notation. So this is saying now that we're saying a sub 1 then is going to be 1 times 3 times 5. And that's going to be 15. And a sub 2 is going to be 2 times 4 times 6. That's going to be 48. And let's just do one more. A sub 3 is going to be 3 times 5 times 7. 5 times 7 is 35, times 3 is 90, plus 15 is 105. Isn't my sigma then going to look like this? My sigma notation for S sub n is going to look like this then. In I as the index, I equals 1 to the n, is going to look like this now. The index I equals 1, all the way up to n. And as we look at our a sub n, that turns this into this then. So we have I times I plus 2 times I plus 4. So we need to multiply that out. And that's going to look like this now. The sigma notation as I equals 1 to n of I times I squared plus 6I plus 8. And let's kind of clean that up a little bit. Isn't that just going to be I to the third plus 6I squared plus 8I? And here's our sigma notation. So as we are evaluating this now, we are looking at a sigma notation as it's acting on a sum. And as we're doing that, isn't that going to do this now? It's going to be I equals 1 to n, and I'm going to copy that because I'm going to use it again, of I to the third plus, and we're going to write it this way, 6 sigma times I squared plus 8 sigma I. We're reminding ourselves then of the sums of powers of integers, and those first three sums that we shared with you earlier in this talk. So we have I to the third, and we know that when we evaluate that sum, it's going to look like this: n squared times n plus 1 squared over 4, and plus 6 times n times n plus 1 times 2n plus 1 all over 6. So those 6's actually cancel. Plus 8 times n plus 1 over 2. And that 2 cancels with the 8, and that becomes 4. So if you look carefully now, as we're looking at this version of S sub n, that we can clean this expression up a little bit. We can actually factor out n times n plus 1 out of each of the sections here. So we're going to do that, and then we also see that there is a greatest common factor of 4 down in the denominator. So as we do that, we're going to say n times n plus 1 over 4, and that factors out. And I'll put a big bracket in here so that we can say n times n plus 1 plus, and we're going to put a 4 down here. That means we need to put a 4 on top. 4 times 2n plus 1. And then down here, we need a 4 on the bottom, so we need to multiply by 4 on the top. And we really already factored out the n times n plus 1, so that's just 4 plus 4, and this becomes 16. And so now we just keep on working. This is going to be n squared plus n plus 8n plus 4 plus 16. And outside is n times n plus 1 divided by 4. And continuing, n squared plus n plus 8n is 9n plus 4 plus 16 is 20. 4 times 5 is 20. So this becomes n plus 4 times n plus 5, and we're done. So this becomes n times n plus 1, and all of this is over 4. So let's move this out a little bit and recognize that that is our expression for the formula for the nth partial sum, S sub n. So in example 3, now we're talking about this expression here, where it says we're going to do these three things again, only we have 18 plus 32 plus 50 plus 72 plus dot 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 to a sub n. So what does a sub n look like then? Well, let's see. I see this, that I can take out 2, and if I factor out a 2, I'm looking at 2 times 9, and I'm taking out 2 times 16, and 2 times 25, and 2 times 36. So how about that? We have 2 times a squared number. So what we can do then is we can actually say this. We can say that this is saying 2 times 3 squared plus 4 squared plus 5 squared plus 6 squared plus dot dot dot. And there we have it. So isn't this, as we finish out the dot 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 to the nth term, then doesn't this look like this now? It becomes, as we rewrite this, we're really saying 2 times n plus 2 squared is a sub n. There, so I think I answered A. And then the next thing is to rewrite the formula in sigma notation. So now we're going to write this in sigma notation, so it's going to look like this. So down here, this is going to be I equals 1 to the n, and isn't that now I plus 2 squared is written in sigma notation, but now I think we should expand that out. So why don't we do this? We're going to expand out I plus 2 squared. So that's going to be I squared plus 4I plus 4 as we multiply that out. Let's put in our index, and there we have that. And so doesn't this write out now like this? 2I squared plus 2 times 4, and I is inside, and then plus 2 times 4 times the sigma. So as we evaluate this now, this all looks like this. 2 times n plus 1 times 2n plus 1 over 6 plus 8 times n plus 1 over 2 plus 8n. And let's see what factors out of this. If I cancel this 2 with the 6 and get 3, I see and this becomes 4 when I cancel out with the 2. I see a greatest common factor of 3. So I can factor that out, and I'm going to say n over 3. And let's see what factors out. N plus 1 times 2n plus 1 plus, we need 3 down below, so I need to multiply by 3. And that becomes 12 times n plus 1 plus, I need a 3 down below, it needs to multiply a 3 on top, so that turns into 24. And the n already factored out. So there's that. Let's go ahead and multiply this out to continue our simplification. So I get n over 3, and I have 2n squared plus 3n plus 1 plus 12n plus 12 plus 24. So if we drop those parentheses, we get 2n plus 3n, 3n plus 12n. So we get inside 2n squared plus 3n plus 12n is 15n. And I've got 1 plus 12 is 13, plus 24 is 37, and an n over 3 outside. And so there we have it. There's our S sub n over 3 times 2n squared plus 15n plus 37. And that is the sum, the formula for the nth partial sum of S sub n. So here's our homework. I've provided for you a worksheet that you need to download, and I've also provided for you a PDF set of my notes here. so that you can look at the work that we've done to get to this. But there are 12 problems right here. I want you to do these numbers: 1, 2, 6, 7, 8, 11, 12, 22, 23, 25, 29, and 31 on the series worksheet. And refer back to this video in order to get some help. And also give me a call and come see me in study hall to ask questions. And I'm happy to address them. So that's it. We'll see you later.